Hello students, in this video we will study what is the moment of inertia and how to find it. So suppose we have linear motion. So in linear motion, inertia is defined as a tendency of an object to resist change in its state of motion. So greater the mass of the body, the greater its inertia, as greater force is required to bring desired change in the body. Thus mass of the body is taken as a measure of its inertia for linear motion. So inertia depends on mass of a body for linear motion. Now suppose we have rotational motion. So similarly, a body capable of rotating about an axis possesses inertia for rotational motion. The greater the couple or torque, that is an angular force required to change the state of rotation of the body, the greater its rotational inertia is. This rotational inertia of the body is called moment of inertia of the body about the axis of rotation. So let us consider these two cases. We have these two objects having different masses and they are rotating about the axis in anti-clockwise direction. So you can see here the required force depends on the mass of the body. Okay, so in the first case when we have less mass, so comparatively less force will require to bring desired change. Thus, the moment of inertia is the rotational analog of mass in linear motion is depends on mass of the body, but not only on mass. Look at here, suppose we have this third case. In this case, the second and third case, we are having a body with same mass, but the distance of the body from axis of rotation is less in third case. So in third case, if you rotate the body about the axis, comparatively will require less force compared to second case because the distance of the body from axis of rotation is less. So moment of inertia depends on mass of the body as well as it depends on the distance of body from axis of rotation. Now we will see how it depends on mass and axis. What is the relation there? So we will give this relation by using kinetic energy. So here we will compare kinetic energy for linear motion as well as rotational motion. So suppose in linear motion we have this body which is moving along this path. So with a linear velocity v, and in rotational motion we will assume that this body which is rotating about the axis with angular velocity omega. So here we know the relation between linear and angular velocity. V is equal to r omega, where r is the distance of the body from axis of rotation. So for kinetic energy in linear motion, we'll assume that the body is made up of n number of particles, small particles, each having mass mi. So the total kinetic energy will be sum of kinetic energy of every particle. So therefore K is equal to 1 half m1 v1 square plus 1 half m2 v2 square and so on. Now because we have a linear motion, every particle will have same linear velocity and therefore we get K is equal to 1 half summation mi into v square, and the summation mi represents mass of the body. So therefore K is equal to 1 half mv square. This is what kinetic energy for linear motion. Now in case of rotational motion, K will be again same 1 half m1 v1 square plus 1 half m2 v2 square and so on. Now we know that V is equal to R omega. So Vi is equal to Ri omega I, but for rotational motion we have same angular velocity. Linear velocity Vi may be different, but the angular velocity for every particle is same, and therefore we get this K is equal to summation 1 half mi omega square Ri square. So K is equal to this because omega is constant. Now let us call this bracketed term as I. So we get K is equal to 1 half I omega square. Now you compare this. K is equal to 1 half mv square is a kinetic energy for linear motion, and we got here K is equal to 1 half I omega square, which is a kinetic energy for rotational motion. So you can see here this mass here is nothing but this I in the second rotational motion. So moment of inertia, that is I, is the rotational analog of mass, and it is given by I is equal to summation mi ri square, which is equal to integration of r square dm, where dm is the mass of small particle. Now we'll see parallel axis theorem. So here, suppose we know moment of inertia, that is ICOM, that is for moment of inertia of an object of mass m like a ball or a disc, and the axis of rotation passes through center of mass of an object. So we know moment of inertia of this object where axis of rotation passes through its center of mass. And suppose you want to find moment of inertia about an axis which is parallel to this axis. So how the moment of inertia for first case and second case are related. So here let d be the distance between these two axes. Then moment of inertia about this parallel axis is equal to moment of inertia in first case plus d square m. So this is what parallel axis theorem is. Next is a perpendicular axis theorem. So for a planar object, we apply perpendicular axis theorem only for planar objects. The moment of inertia about an axis, let's say z, perpendicular to the plane is, so what is the plane here? XY plane. So suppose our object lies in XY plane. Let's say, consider this circular disc. We have to find its moment of inertia about Z axis, which is perpendicular to the plane of disc. So here the moment of inertia about Z axis is equal to sum of moment of inertia about X axis and Y axis. So Iz is equal to Ix plus Iy. This is the perpendicular axis theorem is. Now we'll see moment of inertia for three different cases. So for a solid, for plane area, and for arc. For solid, mass is equal to density into volume. For plane area, mass is density into area. And for arc, mass is density into arc length. So for solid, m is equal to rho into v. For plane area, m is equal to rho into a. And for arc, m is equal to rho into s. So therefore, for solid, dm is equal to rho into dv. For area, dm is equal to rho into dA. And for arc, dm is equal to rho into ds. For a small particle, density, that is rho, will be constant. We have this formula for moment of inertia. Therefore, moment of inertia for solid is triple integral over v r square rho dv. Moment of inertia for plane area will be double integral over a r square rho dA. And for an arc, moment of inertia is integral over arc r square rho ds. So these are the formulae to find moment of inertia for different type of objects. Now we'll see how to find dv for solid, that is a volume element. So for Cartesian coordinate system, dv is dx, dy, dz. For spherical polar coordinates, dv is r square sine theta dr, d theta, d phi. And for cylindrical polar coordinates, dv is rho, d rho, d phi, dz. For plane area, we have to find dA, that is the area element. So here for Cartesian coordinates, dA is dx into dy, and for polar coordinates, dA is r into dr into d theta. Now third case, for arc we have to find ds. So for Cartesian we have this formula to find ds, and for polar we have this formula to find ds. In Cartesian, when y is a function of x, ds is this under root 1 plus dy by dx square into dx. When x is a function of y, ds will be under root 1 plus dx upon dy square into dy. And when we have parametric equation, x is equal to f1t and y is equal to f2t, ds will be under root dx by dt square plus dy by dt square into dt. And in polar, when r is a function of theta, ds is under root r square plus dr by d theta square into d theta. And when theta is a function of r, ds will be under root 1 plus r square d theta upon dr square into dr. And for parametric equations, when r is function of t and theta is also function of t, ds is under root dr by dt square plus r square times d theta upon dt square into dt. So this is how we can find dv, da and ds. Thank you.